General relativity relies on a smooth topological manifold to describe the universe, but if you zoom in far enough, that continuous surface fractures. It crystallizes into a rigid, jagged network of interconnected nodes and lines. Quantum field theory is built on mathematical operator algebras. By its very nature, it is strictly discrete. You cannot map discrete quantum operators directly onto the smooth background grid of general relativity without creating immediate mathematical contradictions. Standard discrete gravity models like loop quantum gravity or causal dynamical triangulations force these two regimes to merge. The result is severe anisotropic shear and unresolvable Lorentz violations. Achieving true Lorentz invariance requires a complete departure from effective field theories. We have to drop the assumption of a continuous background entirely. The unified dynamics framework demotes the spacetime manifold. It is not an objective physical fabric. The continuum is merely a low-resolution statistical compression algorithm summarizing local path accessibility. What you are seeing here is the true fundamental substrate, a pre-geometric graphite network, casting a perfectly smooth, continuous drop shadow onto a flat plane beneath it. We can derive the continuous Vierbein directly from discrete tetrahedrons, resolve the boundary mismatches between matter and geometry, and isolate the exact computational genesis point of the Big Bang. By treating spacetime as an emergent property, physical observables become strict combinatorial invariants. This animation shows the fundamental building block of the framework, the background-independent K4 simplicial primitive, a 4-vertex tetrahedron suspended in an empty void. Physical observables in this system are derived strictly as native geometric invariants of this exact graph structure. We trace a path cycling endlessly through the 6 edges of the tetrahedron. This repeating closed one-cycle is the simplicial holonomial circuit. The localized frequency of this non-trivial holonomy maps mathematically to invariant rest mass. Particle mass shifts from an arbitrary scalar assigned to a dimensional point into the required frequency of a structural topological loop. We shift our analytical focus from the connecting edges of the network to the computational behavior of the isolated vertex nodes. At each specific node, we track the vertex state update density. The local density of these discrete computational state updates generates the mass energy distribution tensor. As updates process across the interconnected complex, a discrete accessibility gradient emerges. This creates structural regions of high computational debt. This routing gradient exerts topological boundary pressure. Macroscopic physics subsumes this pressure as geometric attraction, or gravitational acceleration. Gravity and mass energy are not external forces acting upon a grid. They are the localized computational processing deficits of the vertices themselves. Expanding outward from the single primitive, we reach the S3 cubic coarse-graining shell shown here. It contains exactly 18 distinct vector arrows radiating from a central point. These 18 vectors represent the local, unaveraged discrete transport directions within the shell. At the microscopic scale, network transport along these paths is jagged, highly directional, and entirely anisotropic. We assign the binary Z2 chiral framing to these edges, represented here by alternating +1 and -1 polarities. We visually collapse these 18 vectors into a single mathematical summation. As they merge, the alternating Z2 symmetry forces the off-diagonal anisotropic shear elements to self-annihilate. The result is a perfectly smooth, translucent, flat 2D tangent space passing through the center. This isotropic matrix yields the exact algebraic derivation of the continuous Vierbein. A locally flat Minkowski space natively emerges strictly as a statistical equilibrium. Lorentz invariance is secured without phenomenological smoothing. Mapping a discrete graph to a continuous manifold historically creates a topological mismatch known as the C2 real anomaly. In this diagram, you can see the glowing vertex nodes representing matter fields floating entirely out of phase with the bottom grid lines representing geometric matrices. We introduce the mathematical constant 1/9 pi squared into the empty space between the layers. This constant exerts a pulling force, physically compressing the distance between the two structures. The top nodes perfectly snap into the intersections of the bottom grid lines, locking the framework together. This specific metric compression factor is the classical Einstein coupling constant. Gravity functions as the temporal glue required to pull this structural mismatch to zero. The Einstein constant possesses its exact value because it is the necessary ratio to achieve structural alignment. This plot tracks the F6 falsifier pipeline, a stress test of 800,000 samples. At n equals 6 and below, the line remains flat, an unclosed computational vacuum. At exactly n equals 7, the topological closure rate spikes to 94.07%. This massive statistical jump at the n equals 7 boundary acts as the combinatorial genesis event. The framework mathematically mandates the discrete equivalent of the Big Bang. It resolves the vacuum state transition without relying on continuous cosmological inflation models. The framework enforces an epistemic firewall. This mathematical boundary separates combinatorial geometry from arbitrary dynamic variables. Respecting this firewall yields 28 exact zero-parameter predictions for physical observables. The foundations of both general relativity and gauge theory emerge entirely from the symmetric group permutations of the K4 simplex. By discarding the assumption of a continuous background, unified dynamics bypasses the arbitrary free parameters of effective field theories, offering a mathematically falsifiable resolution to the hierarchy problem.